We have been discussing the solution of Poisson equation using the Green's function technique. So let me remind you a part of it. And we also said that though we are discussing this in terms of Poisson equation, which is a valid case for the electrostatics and magnetostatics, this method will work if you have a similar setup with any linear differential equation, linear partial differential equation. So the Poisson equation is grad square phi equals minus rho by epsilon naught. So this is, just let me remind you again, this is a linear equation and inhomogeneous equation. Inhomogeneous means that I have a term which is non-zero and does not contain phi, which is what we are trying to solve for. So we are trying to solve for this. And this is the source which is known. Where it is known? In a volume. What else? Boundary conditions. That is also known. Now, this is the question that we are asking. The way we answered it is, of course, using Green's method. So we introduced something called a Green's function, which is a solution of an equation which has the same operator the solution we call G, but a delta function source. And as we have seen, the boundary condition for G is chosen according to our convenience. Further, we did one more thing. We said that we can break G into two parts. One of these, so let me write G, so that is x prime. One of these I call G prime, other I call F. At this point, I should remind you of the setup. The setup is that I have a finite volume V, which is surrounded by a surface S. So this is the setup for our original Poisson equation. So let me keep the setup at the place of the Poisson equation here. So I have a finite volume V which is surrounded or covered by a surface S. Okay, the boundary conditions are the conditions known at Cs, and the sources are known inside the volume, so at V. Okay. Now, as we are writing down a different equation, which is of the Green's function, we say that this for a boundary at infinity. So that the boundary is at infinity. In 3 dimension, we'll choose the value of the Green's function to be 0 there. So this only depends on the operator. So this, in case of Laplacian, is mod of x minus x prime. This, on the other hand, depends on the boundary. So G has a boundary condition, F will depend on that boundary condition, and F is a solution of this equation with that boundary condition. So the boundary condition will be on G, that is what I will choose for a given problem or a given type of problem. Once I choose the boundary condition of G on G, G prime is already known, so this is depending on the operator. We saw how to get to it in the last discussion. So this is G prime is known, so boundary condition on G directly gives me a boundary condition on F, and I use that boundary condition with the solution of Laplace equation to get what is F. Once I know F, I know G prime, so I know capital G. What do I do? Okay, so let us now choose a particular type of boundary condition, because that is what we will discuss today mostly, which is Dirichlet boundary conditions. As we have been saying, that the choice of the boundary condition on G is on us, and in this case we choose this equals 0 at boundary. So as a consequence, we need to know phi at the boundary. Okay, so that will be enough. If I do all these, now the general solution, the solutions to phi. So till now I have been dealing with solving a problem that I created, which is this one. But we are interested in solving the original Poisson equation. So the solution for that Poisson equation now can be written this way. And as I said that today we are discussing only the Dirichlet boundary condition. So I am only writing for the Dirichlet boundary condition. We'll be not discussing the Neumann or Cauchy any further in this course. Obviously, you need to get familiar with those, but In the discussion sessions, we will not be discussing. So this is over a volume V. This is over the surface which is enclosing the volume, and what all I will have here is phi prime is the phi. Okay, so let me not write phi prime, you may consider it derivative. So it's a phi s at the surface, obviously, because that's a surface integral. So what does it give us? So we'll see some examples today, but let's understand what has happened. This is only we have discussed last time's things so far. So we have this Green's equation, which gives me the solution of which is Green's function. And we said that the solution can be written in terms of two parts. So one is always 1 by mod x minus x prime if the operator is Laplacian. The other will depend on the boundary and what boundary condition I choose. On capital G, grad square f equals to 0 with that boundary condition will give me what is capital F. Once I know capital F, f plus g prime is my boundary, is my Green's function. And all I need to know of G is to know what is the boundary condition on F. And what is the boundary condition on F comes from the boundary condition on G itself. So if I choose a Dirichlet boundary condition, which is whatever at my boundary, and this boundary will be chosen to be the boundary of the original problem. So the original problem, which is this, has to be a boundary condition, obviously, to solve a partial differential equation. And whatever that boundary is, whatever the geometry of that boundary is the same for when I say capital G equals to 0. So which also means that, so this we call the Dirichlet boundary conditions, wrote with a suffix D, but because we are dealing with only Dirichlet Green's function today, we are not writing the D explicitly. So everything is Dirichlet for today. So F depends only on the shape of the boundary, or should I write geometry of the boundary? Remember, this is the same boundary that is of the original problem. So because that boundary is known, now I know what is capital G in principle. If I am good in mathematics, obviously, solve for Laplace equation, use that boundary condition, I know capital G. And then I can write down the solution for phi. So solving for phi, apart from doing these integrals, which may or may not be trivial but can be doable, solving for phi boils down to solving for f given the geometry of the boundary, and f follows a Laplace equation. So let me write it here. Solving for phi boils down to solving f when grad square f equals 0. So that's a Laplace equation plus same boundary as the original problem. So this is what simplification the Green's function gives you. Okay, so now saying all these, let us look at applications for this. Now it's obvious that sometimes we even don't need to solve the Laplace equation. We can use some certain symmetries of the system to solve for these boundary conditions, solve for f. Okay, so let us consider an example. It's a point charge q naught at a distance d from an infinite conducting plate. Kept at a zero potential. Well, when I say zero, kept at a zero potential, this is equivalent to grounded, right? Because ground is usually taken to be zero potential. So this is a grounded infinite conducting plate in front of which you have kept a point charge. So probably this problem you have seen infinite number of times now, but still let us look at in the perspective of the Green's function technique. So I have this charge which is at a distance d, and immediately you see that if I draw a perpendicular to this, so that is that along that perpendicular the distance is calculated, but that gives you a symmetry axis also. So this is also a symmetry axis of the problem. Because if I go anywhere around this line, if I rotate the system, you will see the value of the potential cannot change. What is G for this? So this is, by the way, this is the original problem. So I can write rho here. This is q naught times delta x minus x1. x1 is related to the position of the charge. So we have to really choose an origin for this coordinate system, and then we can talk about what is that in terms of the origin. Now, let's see what are the symmetries that I have in the system. First of all, let us choose an origin. Obvious choice of the origin is here, where that perpendicular intersects the plane. So I can choose this to be my xy plane, and this as z axis. So then x1, which is the location of the charge, is essentially dz cap. And if I want to calculate the potential at any point in x, you see my charge is here. So this is the location of the charge q naught, which means my volume is this, and my surface is the grounded conducting sphere, sorry, grounded plane, because beyond that I don't have anything that I can measure, but at the plane I am given what is the potential, which is 0. So if I take any other point where I want to calculate the potential which is inside my volume, so that x is essentially so one thing I realize that I have a symmetry in the problem about z axis. In principle, what you now need to do is to solve the Laplace equation of f by demanding at the surface g is having a certain value. So let's see what is g at the surface. Z equals to 0 by definition at the surface. So g, and so gx, so this I take a vector at the surface. The radius vector at the surface. Radius vector is one which starts from the origin, if you remember. This x prime is 1 by s minus x prime plus I know what is the value of phi in my original problem. There is given to be 0 at the conducting plate. So that corresponds to a Dirichlet boundary condition. Even if I am using a Dirichlet Green's function, so this is equals to 0 at the boundary. Now for this case, it is easier if I use a guess to find the form of f. And that is, it used to be k by s minus, or because I'm choosing f, so let's write this first, x minus alpha x prime. Okay, now so if I use that there, this x has to be replaced by s now, because I'm doing it at the surface now. Now, what is the denominator in the left hand side? This is a square plus x prime square minus 2 s x prime. And if I consider the angle between them, what is the angle between them? Well, x prime is this vector, s always lies on the surface, so the angle between them is 0. So this term I don't need to write down. Square root of this is mod x minus x prime. So if I just square that, so I get s prime plus x prime square. The right hand side I get a square plus alpha square x prime square. You may think what I have done is I have written it this way. That is quite legitimate to do. And then I have squared them. So I get this, and I also get k square equals 1. For this to satisfy. You may be asking, how can I just guess a solution and then figure out what is capital G? And once I have been successful doing that, then you will see that the beauty of one theorem that we proved last time. So what do we get here? What we get here is that either, so alpha square is plus or minus 1, and I'm sorry, alpha is plus or minus 1, and k is also plus or minus 1. Okay, and remember that you have to satisfy this. This is not equals G anymore. So I have to satisfy this. So let's see what I can get. So let's choose k equals 1. And alpha equals 1. So what happens to G now? So G x prime, k and alpha both are 1. So I put, okay, so I completely remove G from the equation, but I can keep it here. So this is G x prime, if you remember, was 1 by mod of x minus x prime plus k by x minus alpha x prime. Right, so this was G. So if this is my G, k equals to 1, alpha equals to 1, okay, so k equals to minus minus 1, alpha equals to 1. So let's take that choice. So what I get for G is that G is 1 by mod x minus x prime minus 1 by mod alpha equals to 1. So this is x minus x prime again. So G is 0 everywhere. That's a trivial solution. Obviously, that is not the case. So let's choose k equals -1, alpha equals -1. So then I will get a g which is x prime. This will obviously, this is g prime, and this will be alpha -1. So this is x plus x prime. Well, that's a legitimate solution, because see what happens if I put these things at the boundary, then you will see that this is going to 0 at the boundary. Okay. How do you see that? Well, obviously this it will satisfy, and if it satisfies that, it will be 0 at the boundary, because that's how I get those. Now once I got such a solution, then I am done, and that's the beauty of it, because G is the solution of its own Poisson equation, which is here, given the boundary condition and that G equals to 0 at the boundary, and that solution is unique, that we proved last time, which means that once I have got such a solution, it's unique. So what is rho? Sorry, what is phi? Now it is trivial to get what is phi. Just put it inside our phi generating machine, which are a couple of integrals. First, there is a volume integral, and the volume integral I will put this now as my g. My rho was q naught times delta of x minus x prime, and then I have a surface integral which is del g del n prime, which I have not calculated, but at the surface phi equals to 0. So this time 0 dA prime. So obviously if I multiply anything by 0, it's going to be 0 only. So what I get here after doing the integrals, charge is at 1, and that's all. There is a catch here. I had a volume integral over a certain volume V. It's not a volume integral which goes to infinity. But then how come I do this delta function integral? Because for the delta function integral to work, the volume integral has to go to infinity. I can do that because this x1 is guaranteed to lie inside my volume. So because I am not introducing any charge here which is outside my volume, so let me write it here explicitly. I can do the above volume integral by shifting the integral limit to infinity. Why is this? This is because x1 is guaranteed to be so remember x1 is the position of the charge in my problem, in my Poisson problem, and that charge is obviously inside my volume. That's how the problem is defined. So if that is inside my volume, I have only one charge. If I would have had 5 charges, all 5 charges are also inside my volume. If all the charges are inside my volume, there is nothing else outside. In terms of when I look at in terms of rho, then this volume integral over the outside is 0. So that is why I can push this boundary to infinity. That also we discussed briefly last time, but here we see it in effect explicitly. But now I can also see these two integrals in a little different way. So I can write this just by doing some mathematical manipulations. I can write this in terms of two integrals. In both cases, the Green's function is only this. And then I have x minus x1 plus another integral. You see the Green's function remains as it is. The density now is this. Okay. The first integral is exactly the same. In the second integral, what I have done is I have used the property of convolution where I can change the variables. Okay, let's not look into it that way. But you see, if I do this integral, the second integral, I will get minus 1 by x plus x prime, because now so these are x primes. Sorry, x primes will be replaced by x1. Yeah, so these are x primes. Sorry. Now x primes will be replaced by x1, so I will get exactly the same solution as this. This is the case for 2-point charges. One at x1 charge q0. I'm sorry, these are q zeros, not rho zeros. And other at minus x1 minus q0. Right? So this essentially is the case in the following case, that this is my xy plane now. Sorry, this is xy plane. Z axis. Two charges. And the potential for these two charges is what the potential that you got for the case where I had this grounded infinite conducting plane and one charge here. Immediately you learn one thing, that given message, this is a very important message, given a solution, the charge distribution and the boundary conditions are not unique. Now this also gives us a new way of looking at the problem, which we know as the method of images. So this is the origin of the method of images. So what do you do in the method of images? Imagine that I am said that, okay, so this is let's look at the similar type of problem. I am said that there is a charge of plus q kept here and there is a charge of minus q kept here. Find out, and there is an infinite grounded conducting plane there. Find out the potential everywhere in the right side volume. What you do is that you say that, okay, first of all, I know that the superposition principle works, so I will do charge by charge. I will first forget one of these charges. I will take that charge. I know that corresponding to that, I can remove the boundary and put another minus q charge over there at the same distance from the boundary. If I solve without the boundary and that only the plus q charge up here, if I put this minus q charge there and solve for the potential, I'll get the exact same potential in the right hand side. Then you say that, okay, so now I can repeat the exercise for the minus q charge. So for that I need to put a plus q charge here at the same distance from the boundary again, and I can solve the potential for these two charges, and once I am done I can just add these two potentials. Or what I can do is that now I have these two charges and their images. I can solve the problem for these four charges. So that's the celebrated method of images. It's a very trivial example with the method of images, but it just comes out of the Dirichlet boundary condition. Exactly this the problem that we have discussed here. So that concludes our discussion today. We have seen how to solve the Poisson equation for electrostatics problems, and also only for a particular case, which is for the Dirichlet boundary conditions. We'll see other examples in the next lecture, and then we'll also see, we'll kind of try to generalize this for the dynamics case. Thank you.